So even without the handout being single-sided there, it's a pretty big section because it's a pretty important idea here, which is why they call it the Fundamental Theorem of Calculus. If you read in the textbook, they really try to convince you that it's an earth-shattering, amazing idea, and often when you're reading textbooks, that doesn't come across. You have to think about it in terms of before you had computers and calculators and all this stuff that can do anything you want, this was a pretty revolutionary discovery or idea, because it allowed you to go from before. I mean, the development that you've gone through here is getting you from the idea that you started by looking at areas under curves by approximating them with rectangles, right? And that was kind of tedious to get detailed or accurate answers if you wanted to, especially if you didn't have any kind of calculators or anything. But where you're going in this is you're getting to the point where you can evaluate the area underneath a curve in a really simple calculation with this called the Fundamental Theorem of Calculus. There's two parts to it. And you had a hint at the first part in the activity you did last time, where you were picking an x value, shading up to that point. If you look at the first part here, anytime you put things in notation like this, it looks complicated, but it's not, okay? Especially given that you worked with it last time. This is a function like the one you used in the activity you did last time, where you have a function that is defined with an integral, right? It's the integral of a function here. And we talked about why you had to use a t here instead of an x, just because you're using x here as the upper limit of integration, as in the point where you stop, right? So if you go back to that picture and just think about it again here, this picture. Okay, you guys picked an x value somewhere, and then you shade it up to that point. I'll do a really bad job of it quickly here. And you were using a ruler, you were shading it in with vertical line segments, and you got to there. That was the function value of this. You needed you could have put a t here and just called this axis t, because you're using x to mean this specific point. So if you have that, you're looking at now, what's the rate of change of this function? If capital F is the area, okay, you can think of it as the area underneath the curve. What's the rate of change of that? Well, you looked at what the meaning was last time of what the rate of change of that was, and you found that it's just the height of this function at that particular point. Okay, so if you go back to this, where we have it written out here, this says a couple different things here. Whoops. First of all, it says if you have some function that's continuous, then this function has a derivative at every point there. Okay, this function is the integral of that function. It's an antiderivative of that function. And then if you have the derivative of that function, so if you have the derivative of the integral of this function, it's just the function itself. And that's what you hopefully got out of the activity that you did last time, but it's put in more formal terms here. Essentially, it's saying derivative of the integral of a function is the function itself. Now, specifically, it's related to that upper limit, that point that's moving. Okay, it's not related to the fixed point at the beginning. And the reason we did the activity first is this is really hard to understand unless you've done it in concrete terms like that. It's related to that. It's just a function of that variable limit. Okay, so it says a few different things here. It says that every continuous function is the derivative of some other function. And every continuous function has an antiderivative. And maybe more importantly here, what it does is, or most importantly, it ties the two kind of branches of calculus together, integral calculus and differential calculus, by showing that they're inverses of each other. Before the development of this idea, looking at slopes of tangents, right, which is what we were doing when we were doing derivatives, differential calculus, you're looking at slopes of tangents, and here we're looking at areas under curves. There's no obvious reason why areas under curves and tangent lines are connected in any way to each other, but that's what this theorem does, is it shows that those two processes are inverses of each other, and they're intimately connected together. Okay. The other thing, or the last thing that it says here, is that if you have the derivative of the integral of a function, you can find it by just saying it's the function itself for the upper limit of integration. It's a function of its upper limit of integration. Right? So it says a lot of things there. More or less the key one is this: knowing they're connected together and knowing that derivative of integral of a function is the function itself. Okay, we're going to look at kind of a proof of this here. This is in the textbook, but we'll look at it together here. If you do want to follow along in the textbook, that would be great. To be able to do this, you first of all need the definition of the derivative. We are looking at now, what's the derivative of this function? A to x f of t dt. We're looking at what that is, right? That's what we want to do. Okay, capital F refers to that function. We want to know now what the derivative of that function is. Right, because the theorem says, derivative of this, derivative of that is the function itself, right? That's what we're trying to show here. In the end, we're trying to show this is just equal to f of x. It's equal to the function itself. That's what we want to show. If you start with the definition of the derivative, I don't know if you remember that thing that's limit as h approaches 0 of f of x plus h minus f of x over h. Do you remember that thing from long ago? Seems like an eternity now. But this is kind of weird because this function is defined using an integral, but you can still write out the definition with something specific for each of these. You can write out something for each of those. All right, what can you write for each of those? Well, the first part, or the first one, f of x plus h, is just integral from a to x plus h, right? And the second part is integral from a to x of that whole thing, right? The whole thing's over h. Now remember, this is where we're going eventually, but we'll leave that over at the side there. Get it back later. Now you can use some properties of integrals to simplify this thing on top.
Now specifically what I mean by that is you can combine these two integrals. If you have this integral from a to x plus h, and you have this integral from a to x, think about it if you had it on an axis. I'll draw a little thing over here. A, x, x plus h. If you had just any old integral here and you had the area under the curve here, so if you have one of the integrals is a to x, the other one is x plus h. If you're subtracting the blue minus the green, so all the way there, take away, I guess it was yellow to start with, take away this part, the part you have left is that blue part, and that you can write as the integral from x to x plus h. So we can write this as limit as h approaches 0 of integral from x to x plus h of f of t dt. Now, I could put divided by h like I did before there, but I'm going to write it like this instead. Instead, I'm going to say 1 over h times that, just to keep it a little simpler. Now, you may not recognize that, but this actually looks a lot like an expression you've seen before. It's actually the expression for the average value of a function. So let's get rid of this here. And let's just have 2 points labeled. Let's say this one's x, and that one's x plus h. And the average value of the function, let's actually draw it so that it kind of goes up so we can see a little easier what's going on here. Average value of a function, somewhere in between here, there's a c value if that function's continuous, so that you have that average value there. Like if you leveled it out, if you shook a glass full of sand and leveled it out, that's that average value. And that height is f of c, for some c in between there. So since this function is continuous, there has to be a value that equals this. There has to. There has to be some c value in between these 2 points that equals that. So we can write this as equals limit as h approaches 0 of f of c for some c in between x and x plus h. There has to be a value in there. Has to be a function value in there because it's continuous. Move down a bit here. Now if you say the limit of that as h approaches 0, if you push this all over here, it's just going to carry that down with it. Now let me show you what I mean by this. If you have two points, and this is, so let's say this is a function here, and you have a point x and x plus h, and you're talking about a point in between c where that function value is equal to the average. As you push these 2 points together, as you take the limit as h approaches 0, as you let h approach 0, these 2 points collapse together. If that function's continuous, this is just going to slide along here and become equal to f of x. If you push those together, that f of c becomes f of x. The limit as you make h 0 is they're all the same. They're all f of x. So in our proof, what that means is at this point we can say this has to be equal to f of x, which is what we were looking for it to be in the first place. Or if we're going to write the other side out here, we started with derivative of integral from a to x of f of t dt was just f of x. Right? Now you can use that as kind of a shortcut. There's a couple of quick examples here. Maybe we'll move it down and we can have a bit more space here. Okay, move it down here. Alright. If you're looking for the derivative of this, it's pretty much that exact setup there. Derivative with respect to x of the integral from 0 to x of cosine of t. This says that it's just equal to that function itself of that upper limit of integration. So you can just use a shortcut and say this has to be cosine of x, not affected by that value right there. Same thing with a different function here. You have this function, and you're looking at the derivative of integral. Well, it's just going to be that function itself again. 1 over 1 plus x squared. Pretty simple, eh? Applying that. I don't know why I gave you so much space there. Now, that's just a couple of really simple examples of applying it. You're going to move on to do some more involved things here and combine it with some other integral properties and things, and create some functions and graph them. But that's that for now. Fundamental Theorem of Calculus Part 1.